Aloha class, section 5.3, definite integrals and antiderivatives, okay? Topic 6.6, applying properties of definite integrals, and we're going to define what a definite integral is in this section in relationship to a Riemann sum and limits. So really good, fun stuff, right, Holmes? All right, let's roll. Okay. We have some properties that we're going to have to really make sure we're familiar with. I'm going to go ahead and do some problems and use the properties. But what I'd love for you to do is hit that pause button and really look at each one of these properties and see if you could actually use them, right? We did things like example 1 with properties of limits. And if we look at that integral symbol, remember, it's a limit of like an infinite amount of rectangle. So those same kind of rules that we used for limits, same properties we had for limits, are very similar to the properties for definite integrals. So take a shot at it. Hit that pause button and take a shot at it. Hopefully you did, and here we go. Right? In order to use these guys up here, I have to show that I have that within my problem, which I don't right there. But guess what? Just like the limit of a sum was the sum of the limit, the same thing holds true for definite integrals. So I can break this up because the definite integral of the sum is the sum of the definite integrals. Remember, it's a definite integral because it's defined. It has a lower and a upper limit. So this right here, now I can use substitution, right? Whenever we sub, we should technically use parentheses. So I get a little of that, and 8 is my answer. How about it? Not bad, right, class? I really hope you tried it on your own. Okay, it will stick in your brain a little bit more if you do. Now, guess what? The same thing happens for a difference. Okay, so we do a little bit of that. Remember, whenever we sub, we should use parentheses. So what do we have here? We have g of x, which is -2, minus f of x, which would be the 10, the integral, would be equal to -12. How about it? What about the next guy? Well, we have a constant there, that constant 3. Just like limits, right? We could pull that bad boy out. So believe it or not, we could do the same thing with integrals. So let's pull that bad boy out. And then what does that mean? That means I can use one of those givens they gave me earlier, which the integral from 2 to 6 of f of x dx is 10. And I get 30 as my answer. And our last one, this one's a little bit different. Let's take a look at it. But we can use that little rule again. This definite integral of a sum is the sum of the definite integrals. Oh, snap. They don't give me that, though. What the heck am I going to do? How do I handle this? Well, we all know that we could draw a picture for that bad boy. That's y equals 2, right? That's my function, and it goes from 2 to 6. Well, that's a rectangle, so I can find the exact area, right, Holmes? Okay, so we get a little, what does that be, a 4 by 2. And a 4 by 2, let me show work here, 4 by 2. So that would be a little 10 plus 8. That would be a little 18. I really hope you challenge yourself and you try that on your own, okay? Quit waiting for me. You learn more if you try some of these things on your own. All right, here's a little bit of a different problem, okay? And I guess if you want to try something like this, you can. It gets a little bit rougher here, okay? Because they ask me for the integral from 0 to 7, and they don't give me this. So what we're doing here is we're kind of going backwards a little bit. How could I get from 0 to 7 using some of those things that they gave me earlier? But guess what? Let's say I travel from 0 to 5, right, class? And then let's say I add from 5 to 7. Isn't that the same thing? You better believe it. That's one of those properties on that other page. So that would just be 10 plus 3 equals 13. Oh, snap, my favorite number. All right, here we go. 5 to 0. What? They didn't give me that up there. But guess what? We had a property that we could put a negative out there and we could flip the limits. Oh, sweet. That means I can use that little guy up there. Negative, that's a 10, -10. Boom. I hope I have a lot of these on my next test. Well, this one means I'm going to travel from 5 to 5. How the heck are you going to go from 5 to 5? You can't. You don't go anywhere. So what's your area? It is 0 for the hero, right? And then our last one there, same as before, it's a constant, so we can take a constant out. And I have to take my constant out and able to use this guy right here, which is equal to 10, a little direct sub, and I get 30, right? All right, now we get into a huge idea in AP Calc. And that is our idea of average value. Suppose you wanted to find the average temperature during a 24-hour period. How the heck could you do that? Well, obviously, you're just going to sum up all your temps and divide by the number of temps that you recorded, right? So we would sum up temps divided by number of temps, whoops, that looks like an F, temps recorded, right? We all know how to find the average of everything. Suppose F of t represents the temperature at time t measured in hours since midnight. One way to start is to measure the temperature at n equally spaced times. Like, are we gonna measure temperature every 12 hours? That'd be silly. That wouldn't be a very good average. Maybe every 2 hours, right? Maybe every 1 hour. Would that be pretty good? What would give me the best average? Think about that. Right, Holmes? Okay, think about that for a little bit. All right, but using this method, write an expression for the average temperature, okay? And we're going to do that guy right there, n equally spaced out. So that would be like f of, right? Because let's say we have some function, right? We have f of t being the temperature at time t. So we f of t1, right? Plus f of t2 plus f of t3, right? Those are all temperatures, 68 degrees, 74 degrees, plus plus f of Tn, right? And we're going to divide that all by what? The number of temperatures we had, right, class? Now, the larger the number of measurements, the more accurately this will reflect the actual average temperature. Notice, we can write this expression as a Riemann sum by first noting that the interval between measurements will be. So remember, that means your change in time. Let's say I wanted to make my n 24. The 24 divided by 24 would be 1. So my change in time would be if I did it every hour. What if I just wanted to do it every 2 hours? Right, class? What would that be? I would put a little 12 down there, right? If I did 12 different increments, or I did it from 12 to 2, 2 to 4, there'd be 12 of those, and my change in time would be every 2 hours. Now, it's a little bit easier if we write it like that, right, class? What do I want my change in time to be? Let's say I wanted it to be every 2 hours, right? That'd be 24 divided by 2, your change in time, which I would need 12 intervals, okay? And as you may think, okay, example 4 says, substitute this value of n into your expression above and simplify. They want me to substitute that guy? All right, I'm going to kind of do it up here because I think I'm going to need a lot of work. They want me to substitute that and for that right there. So we have f of t1 plus f of t2. I'm going to stop there. I'm going to go plus that, plus f of tn all over, and they want me to substitute 24 over delta t. Now, if you're like me, I don't like having a fraction in the bottom, so I'm going to multiply by the reciprocal. And I'm going to get delta t times all of those guys, right? I'm going to distribute it. Delta t times, right? F of t2 plus plus delta t times f of tn, right, class? All over 24. Okay? And that'd be a great idea, a great way to find the average temperature. How about it? Let's keep going. The last expression gives us an approximate average temperature as n goes to infinity. Remember, what the heck does that n goes to infinity mean, right, class? That kind of brings up that idea of a limit again, okay? Meaning we are taking a lot of temperature readings. This Riemann sum becomes a definite integral. Well, how the heck does it become a definite integral? Write the definite integral that gives us the average temperature since midnight. So how the heck am I going to do that? So let's think about this for a moment, right, class? And I'm going to turn it into a limit, and I'm going to turn it into a Riemann sum. But let's first look up here before I do that. Well, what the heck is that? That's a sum. Okay, that's a sum, and I can go, let's just go I equals 1 to n, right, class? Or in this case, it almost could be 1 to 24, right? But let's just say n as n goes to infinity, okay? And what we're going to do is we're going to take our function value, I, and we're going to multiply it by the change in t, right, class? And what are we going to divide that entire thing by? We're going to divide that entire thing by the span, right? It's a 24-hour span, right? That's how we would get the average temperature in a day, right? Because there's 24 hours in a day. Now, how the heck do I turn that into a limit, which thus is going to turn it into a definite integral, right? We're going to write, so the limit, okay, as n, just using all the same variables here that I like, as n approaches infinity of, let's go, the sum as I equals 1 to n, okay, we'll call our n, in this case, 24, of f, or I should put an N right there, right, class? I should put an N. F of Ti times delta T, right, class? All over 24. Right? And what that means is I'm just going to have an infinite amount of these bad boys, and I'm going to go like crazy. And I'm just, when I do the limit, it's kind of like, right, the more I have, the better approximation I'm going to get for the average temperature. How could I get the exact average temperature? Well, guess what? I'm going to do an infinite amount of time intervals. So it's going to be like a millisecond. It's going to be like this fast. Right? That's like a millisecond. I'm going to do it every millisecond or even faster than that. Right? That's this idea of limit. And guess what that Riemann sum turns into? It turns into the integral. How about that? And it's going to be the integral from 0 to 24. Okay, right? Because it's in a 24-hour span. It's an entire day. I'm going to have an infinite amount of my time increments, and that's going to be f of t dt. Right? That's what that Riemann sum represents right there. And I'm going to divide that by the length of the interval, which would be 24. And believe it or not, that is going to give me the exact average temperature. Now let's think about this with example 6. Do you think, let's say that's my temperature, f of t, and let's say that's t, and your temperature probably is like that, like last night it was a nice little 58 degrees and we snuggled up under the covers. Okay, it's a nice night's sleep, but then I think today it's supposed to get up to a little 77, and then tonight it's probably going to get back to 60. What the heck would the average temperature be? It would probably be between 58 and 77, right? Homie Holmes, right? And the question is, do you think at any point in time during the day, whatever the average temperature is, let's say it's like 67 degrees, do you think at a certain point in time it's actually going to be 67 degrees? Faux shizzle, my nizzle, right? Why? Because this is a continuous function. If it's continuous function, then there will be some time during that day, during that 0 to 24, that if you have an average temperature of 65, 66, 67, whatever, it's going to hit that. It might even hit it more than once, right, class? And that's what that question is asking right there. That's pretty much the most important concept that we're doing here in terms of average value. Go away. All right. I've got to move my board up. Well, I can come over here and use my finger. Maybe I can't. Boom. There we go. Average value of a function. So easy to get this confused with what we call AROC. Do you remember AROC? Right? AROC is average rate of change. That's the slope of a secant line, right, class? Like an average velocity type of thing. But average value of a function is big time different. That's if we have a function f that's integrable from a to b. The average value from a to b is equal to the integral. Right? We better remember this one. We got to think of a dance for this one. Right, Holmes? What could a dance could be? It could be like an integral symbol, right? Ooh, you didn't miss that. I did it at the end. Integral over the interval. That's kind of like parentheses. No? I'm trying. Integral over the interval. Okay, whenever you hear the word average value of a function, you always want to think integral over the interval. Now, what the heck is all this stuff talking about? What's an average value? Well, we're going to do this example here to help it make sense. I got to get a little water break. Pause and be right back. All right, got my water. Let's roll. All right, example 8. Set up a definite integral to find the average value of y from 0 to 3, then use your calculator to evaluate. I'm going to use that right there. So that would mean the integral from 0 to 3 of x squared dx all over the interval. And that's going to give me the average value, believe it or not. And it says use my calculator. All right, if I use my calculator for that bad boy, I get a little 9 on top. That's what, right? Plug that bad boy in your calculator, divide it by tree. And guess what we get? We get tree. We will learn how to do that by hand in a little bit. Okay, and that is the average value of the function. Average value, whoa, average value of, oh my gosh, average value of the function. Okay, and it's the average value of x squared from 0 to 3. Now let's graph this bad boy. We got 0, 0, we got 1, 1, we got 2, 4. And we got tree, 1, 2, 3, 4, 5, 6, 7, 8, 9er. Okay, and we draw a nice pretty curve through that bad boy. And so what we're doing is the area under the curve is that right there. That'd be 9. That'd be the area. But what's the average value? Well, we divide by the length of the interval, which is 3. And the average value over that span is an answer of 3. Okay? And so it says graph this value as a function on the grid. We did that. Does the function ever actually equal the value? Does the function ever equal the value? Well, the value was 3. Does it? Oh, snap, it does in 2 spots. Plus or minus the square root of 3. If so, at what point in the interval does the function assume it's? Well, from 0 to 3, it would be the square root of 3. Well, where the heck is the square root of 3? Let's go ahead and... That's 1, 2, 3. Square root of 3 is like a little 1.4, so we'll go a little bit there. And I'm going to go up to the curve. Booyah! Oh my gosh, it does! 1, 2, 3. It hits that value. And guess what I'm going to do? I'm going to draw a little rectangle. So if I find out where the function takes on that value, and I draw a rectangle, oh, what are you talking about? Oh my goodness. Homie Holmes, can you believe that? The blue area is 3 times 3, right, Holmes? Is 9, and the red area is 9. That is just cray. But how about it? When I do the average value of this function, I do the integral over the interval to do that for me. I get an average value of 3. If I find out where it takes on that value, which would be the square root of 3, go up to the curve and draw a rectangle, it's the same area. Oh, that's almost too much to take in. Think about that, okay? That's the biggest thing that we learn in this section, all right? Example 10. What do you suppose is a relationship? Oh my gosh, I just kind of answered that entire question right there. So since I answered that question, let's just keep on rolling, right? That example 10 right there. I answered the whole thing. That blue area was equal to the red area. That's kind of crazy to even think about. Homie's over here. He's tripping. Homie's just tripping. All right, here we go. The mean value theorem for definite integrals. See the connection? Mean, average, let's go. All right, the mean value theorem for integrals basically says that if you are finding the area under a curve between A and B, okay, then there is some C. There is some C. So if I find the area of this, okay, I'm going to make that red. I'm going to make that whole thing red, right? We get some answer for that, right? That's the area from the curve to the x-axis. But then that means there's some C between, I'm going to make that blue, right, class, so we can make sure we understand what's going on. I'm going to make it blue. So there's some C, and C does not have to be smack dab in the middle, just like it was in the problem before. It was not smack dab in the middle, okay? There's some C between A and B whose function value, so I'm going to come up here, and I'm going to get that function value, right? That function value would be f of C. Right? That's my y value. And if I draw that rectangle, then guess what? It's crazy, but that blue area is going to be the same as that red area. What is an expression that could be used to determine the area under the curve from A to B? What I want you to do is hit pause. All right, I really hope you hit pause. And the area underneath the curve, hopefully we all know by now, is the integral from A to B of f of x dx, right, class? It says, what is the area of the shaded rectangle, the blue? How the heck do I find the blue? Well, the blue is simply that function value, f of c, right? We're going to call that the average value, right, class? And that is times b minus a, right? That's just a little length times a width. How about that? That kind of looks really, really familiar, doesn't it, class? This value of f of c is just the average value of f on the interval. Now here we go. Let's get into a major definition here, okay? And something that you want to make sure is very clear. And if you're not, you're going to see me in the morning tomorrow so I can clarify even some more, okay? So another way to look at this mean value theorem for integrals is just to say at some point within the interval, the function must equal its average value, okay? So if f is continuous from A to B, then at some point on C, f of C will be equal to, that's average value. Remember, the average value of function is the integral divided by the interval. And there will be some C where it takes on that value. This theorem does not actually find that for you. It is, boom, 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 boom. It is greatly important that you understand the difference between a rock average rate of change, that's the slope of the secant line, and average value of a function. Make sure you have those guys down pat. This, A rock, average rate of change. Slope of the secant line, average value, integral divided by the interval. Whoever does that dance move first in class gets automatic candy. Aloha. See you later.